My name is L Brochard. I'm intensivist in Toronto, Canada, and I'm very pleased to be part of this presentation today with a topic which is a bit unusual. It's about how technology can assist ventilation, and we'll think about especially ventilating patients with ARDS with some perspective on the COVID patient. So my laboratory is working with a number of companies listed here for research grants or for equipment mostly. So during the COVID pandemic, and especially during the first wave, there has been a lot of excitement, concern about the need for ventilators, and an incredibly large number of people who were not in the business of ventilator decided to create new mechanical ventilators. And these are just a few examples, and you may have seen that in the press, because it was sometimes done by very famous people who did not know anything about mechanical ventilation. And this has been interesting. I've been participating to a number of these projects, and it made me realize how the technology about mechanical ventilation was much more complicated than just pushing air in and out. And the question is, which technology do we need, and what's essential? Trying to look for the simplest form of mechanical ventilation in case of a big surge, or also for places where you do not have the air and oxygen pressurized in the walls, so which means out of the ICU. We have been very interested by looking at this small ventilator, which is just authorized for resuscitation during cardiac arrest and after CPR. It's called the Oscillator. It's done by a small Canadian company, and it's just based on a magnetic valve, which open and close at a given set pressure. So as you can see on the photograph, there is no electricity, there is no monitoring. You just need compressed gas, so it can be pure oxygen or it can be with a blender, and it delivers a perfectly constant flow which switches on and off at given pressure. And we added a Peat valve because we thought, well, if we need to ventilate in the hallway a patient with ARDS, we need PEEP. And it was really interesting because it worked quite well with this simple but relatively sophisticated technology. And what worked very well was that the time to reach a certain pressure was very well predicted by the compliance of the respiratory system, which means that from the respiratory rate, you could recalculate the compliance and the tidal volume delivered. So that's could be an interesting use of a simple but again sophisticated technology close to craftsmanship, if you want. Then we went to the next step. We said we have these transport ventilators which are used to ventilate patients during transport, but are they good enough for ventilating a patient with ARDS? And in this study done by Dominique Savary, Jean-Christophe Richard, and the group in Angers, we just look at the accuracy of the delivered tidal volume in conditions of severe ARDS, so mimicking a very low compliance, etc. And we were surprised to see that again, it's pneumatic technology, so there is more settings and monitoring, but it's still quite simple in terms of the possibilities offered by the ventilator, but it's very reliable. So yes, it could be used to ventilate patients with the protective lung ventilation. And even for assisted ventilation, when the patient is triggering, you see that except one ventilator, many of them work reasonably well. So again, we need to think, okay, what are the capacity, what technology can offer? But of course, modern ICU ventilators can do much more, and especially in terms of monitoring, calculations, and the all possibilities given by electronic. And again, these possibilities are now enormous. I don't think they are used so much in the clinical setting, and I think clinicians need to think a little bit about this technology. This is the example of the curves you can get on a ventilator with the flow and the pressure. As you may know, some ventilators also offer additional pressure like esophageal pressure, from which you can calculate the transpulmonary pressure. And I just put this slide to indicate that with an inspiratory pause, you can get the plateau pressure and the difference between plateau and PEEP, which is called the driving pressure. And this is an extremely important pressure. You all know the study from Amato in ARDS showing it's a very strong predictor of survival. This is a recent study by the group in Toronto who find that in all patients under mechanical ventilation, so we are not talking of ARDS anymore, the daily monitoring of plateau pressure gives a very good prediction of mortality. And you see, again, the difference between driving pressure above 5 or above 15 or below 15. And there's a daily association with mortality. So very important monitoring, which is underused, unfortunately. You can do also real pulmonary function testing with the ventilator. This is the classical example of the pressure volume curve. By doing this in patients with ARDS, we realize that in 30 to 45% of patients, the curve does not start until you reach a certain pressure called the airway opening pressure. And the reason for that, it's not because the lung is collapsed. Of course, the lung could become collapsed if you stay like that for very long, for a few minutes, but it's due to airway closure. So the airways are closed. Where is this closure? We don't know exactly, but you see in this patient, this is spectacular. Before the pressure of 16 centimeters of water is reached, the only rise in volume is indicated by this red curve, which is the compliance of the circuit of the ventilator, the tubings. So you just compress gas in the tubings until you reach the opening pressure of the lung. So very important information, I think, for setting the PEEP in these patients, which you can even obtain with a simple pressure time curve by setting the flow at a very low rate, below 10 liters per minute. And you see this this change in the slope, which indicate this airway opening pressure. So very important pulmonary function testing, which can be obtained thanks to the technology of the ventilator. The ventilator is also displaying curves, which you need as a clinician to analyze, because the ventilator is not giving information about that. This is a funny example from the ARDS trial, which compared two PEEP levels, and in the supplement they give this screenshot of recording in one patient, where at the top you have the electrical impedance tomography showing breast stacking repeatedly, and this is asynchrony with double triggering, which is not really detected by the ventilator. So this is up to you as a clinician to look at the curve displayed by the ventilator. So it's something needed to learn. A step further, I mentioned how driving pressure is important. Well, again, it's possible to do these measurements of driving pressure during pressure support ventilation when the patient is really breathing spontaneously with the ventilator. And by contrast with the classical plateau pressure during passive ventilation, which is usually lower than the peak, the plateau pressure during pressure support takes into account the effort of the patient and can become higher than the peak. But then you need a kind of expert clinician at the bedside to say, well, this tracing looks like a plateau, so it's reasonable. You see, this is another example. And when you do that, this is a very nice study by Giacomo Bellani and his group. You see the first graph on the left. There is a clear relationship between the driving pressure under pressure support and mortality, which is not the case for the peak pressure. So technology make it possible, but clinicians have to learn how to do it. And probably the nicest example of how technology can really assist ventilation, it's proportional modes of ventilation. In this paper, we said it assists physiology, and we give the principle of proportional assist ventilation, or PAV plus, and the use of electrical activity of the diaphragm and NAVA. In PAV plus, the ventilator automatically measure, you see this small occlusion on the flow and the airway, measure the plateau pressure again during assisted ventilation, and from this measurement automatically calculate compliance and resistance. So it's a fantastic tool to assist the physiology of the patient. During NAVA, you can monitor the EDI, and this is during a pressure supported ventilation, or you can directly give assist proportional to EDI. This is the NAVA mode. So these are fantastic improvement in technology. And going back to our driving pressure, during PAV, this is very easy to measure because it's done automatically by the ventilator, the driving pressure. And it was interesting to see in this series of patients recorded by Dimitris Georgopoulos and his group that most patients under PAV maintain a driving pressure in a very safe range. You see between 6 and 10 centimeters of water, even if they were initially classified as ARDS. And the last tool, which is now available on most ventilators, is the occlusion pressure, the P01, which can give you indication. And on most ventilators, it works well. You can also do make an occlusion at the end of an expiration to get the negative pressure generated by one breath. Again, the P01 is automated. This one is not automated. You need a clinician at the bedside to do it. Does it matter? Well, this is a really nice study in patients with COVID-19 who had a high respiratory drive after the initial phase of improvement, and a number of patients worsened or relapsed their respiratory failure. And when you look at the daily measurements of P01 or the occlusion pressure, especially the P01, you could very well predict the patients who are going to relapse. So at least it shows that this is an extraordinary useful monitoring which can be used at the bedside to better assist ventilation. So in conclusion, the technology is useful to automatize, to miniaturize, and to provide accurate delivery of ventilation. As I've shown to you briefly, it can assist physiology. It provides essential monitoring during assist mechanical ventilation in general, either passive or active. And that's probably the most important message, the clinicians need to learn what the technology can offer and what they have to do as clinician expert at the bedside. So I'll stop there. I'll be happy to address any question by email, for instance. I invite you to visit our blog, coemv.ca, Center of Excellence in Mechanical Ventilation, to rediscuss all these concepts. And I also indicate a web page, rtmaven.com, where we have provided videos and graphics to explain some of the calculations which I've shown in my talk. Thank you very much for your attention.